Hey guys, welcome to Safi Next. In this video you will learn about three very important concepts of probability theory. Without having the accurate knowledge of these three concepts, the mathematical tools of probability theory may not be optimally applied to real situations one encounters on daily basis. When applying probability theory to real situations, we may encounter complex problems which consist of giant events. In such situations, accurate result can only be obtained if we know about the optimal applications of the two principles of probability theory, that is, the addition rule and the multiplication rule. The applications of these rules depend on whether the events are mutually exclusive, mutually not exclusive, or they are independent events. In this video, you will learn how to differentiate between mutually exclusive, mutually not exclusive, and independent events. Mutually exclusive events are also called disjoint events. Two events are said to be mutually exclusive or disjoint if they cannot happen at the same time. In other words, if two events are such that they do not share a common outcome, they are called mutually exclusive or disjoint. For a more clear perception, let us explain this through an example of rolling a dice. The sample space of the outcomes of rolling a dice consists of 6 numbers in the form omega equals the set of 6 numbers starting from 1 to 6, where each number represents a face of the dice. Although the outcomes of this space are disjoint, as no two can occur together in a single throw, but let us understand the concept of mutually exclusive events through the approach of subspaces. We can split the total sample space omega into a number of different subspaces. For example, one can construct a subspace of the first 2 numbers, or a subspace of the 4 intermediate numbers, or a subspace of the last 3 numbers, and so on. But let us consider subspaces A and B. Each consists of the following outcomes. A is a subspace of omega, which consists of outcomes of the faces of the dice labeled with odd numbers, and similarly B is a subspace of omega, which consists of the outcomes of faces of the dice labeled with even numbers, that is 2, 4, and 6. In this case, the outcomes of subspace A and subspace B are mutually exclusive because in a single throw of a dice, the outcomes of the two events cannot happen together. Mutually exclusive events are mathematically expressed in the form of intersection of the two subspaces and is read as the occurrence of A and B in a single throw equals 0, which also can be interpreted as the subspaces A and B do not share a common element or outcome. On a Venn diagram, they are expressed as two separate circles sharing nothing with each other, like shown in the figure. On the other hand, if the two subspaces are chosen such that C is a subspace of omega, which consists of the first 5 numbers, and B is a subspace, again consists of only the 3 even numbers, then obviously the intersection of these two events is not equal to 0 and is equal to 4. The Venn diagram in this case becomes like this, where the two circles overlap and sharing the element 4. Now events for which the intersection is not equal to 0 are not mutually exclusive events. So events A and B are mutually exclusive, whereas events C and B are mutually not exclusive. In this case, either event A or event B or both can occur in a single throw of a dice due to the shared element, that is 4 in the two subspaces. For example, if the rolling of a dice results in 3, then only event C occurs. If the rolling of a dice results in 2, then only event B occurs. And if the rolling results in 4, then both A and B occurs in a single throw. In both these examples, that is in the case of events A and B and in the case of events C and B, the probability of one event depends on the occurrence of the other event. For instance, in the first case, if the outcome of a throw corresponds to event A, then the probability of occurrence of event B is obviously 0 and vice versa. Now there is another class of events, we call them independent events. Two events are said to be independent if the occurrence of one event does not affect the probability of occurrence of the other event. For example, if we toss a coin and head comes up, this result does not affect the outcome of a second toss of the same coin. In other words, the information of the first toss does not provide any information about the outcome of a second toss. So the outcomes of repeatedly tossing a coin are independent events. Note that unlike mutually exclusive events, the probability of occurrence of independent events are uncorrelated, which makes independent events different from mutually exclusive and mutually not exclusive events.